Hi everyone. In this video I'm going to demonstrate a one-way analysis of covariance using SPSS. Before we get started, let me note that underneath the video description you'll find a couple of links. One is to a PowerPoint containing supplemental information, and the second link will be to an SPSS data file that you can download and follow along with this presentation. So this is the link right here, but again it will be underneath the video description. So let's go ahead and look at our example, and this is just a subset of the data before we actually bother opening up SPSS. So the data set contains an independent variable which is called treatment group, a covariate which is anxiety, basically pre-treatment anxiety, and then the dependent variable is post-treatment anxiety. So we're essentially going to be testing whether there are significant post-treatment anxiety scores as a function of treatment group, and the covariate in the model will be pre-treatment anxiety scores. Just note too that the treatment group is coded in the following way. A value of 1 stands for the control group. It's going to be the standard treatment approach. Then we have treatment A, that's coded 2, and treatment B, which is coded 3. So here we have our data opened up in SPSS, and again there's our independent variable, our covariate, and then our dependent variable. So what we're going to do is go up to Analyze, General Linear Model, and then Univariate. I'm going to go ahead and reset this and walk you through the steps here. We're going to move treatment group to the fixed factors box, post-treatment anxiety to the dependent variable box, and then pre-treatment anxiety to the covariates box. We're going to click on options, and some of the usual things that I will click on include descriptives, effect size, power, homogeneity tests. So we'll click continue there. EM means, that's the estimated marginal means, and so basically when you're running the analysis of covariance, keep in mind that the group means are going to be adjusted for any differences there are between groups with respect to the covariate. So the estimated marginal means will essentially give you adjusted group means. There's the overall adjusted group mean, as well as the overall mean adjusted for the presence of the covariate, and then the treatment group means adjusted for the presence of the covariate. Now if you want to perform post hoc analysis, essentially looking at pairwise differences in adjusted group means, you can't do that through the standard post hoc box that you may be used to when using when you're performing a standard one-way or factorial ANOVA. So there is another way though, using when you're running the ANCOVA, and that's to click on Compare Main Effects. You can use the drop down, and then you can select Bonferroni to get Bonferroni adjusted pairwise comparisons. So we'll click continue, and then under plots I'll move the independent variable over to the horizontal axis and click add. And so what's going to happen is that the profile plot will contain adjusted group means. If I want a line chart, I can leave it set at line chart. If I want bar chart, I can select that. If I want 95% confidence intervals containing the error bars, then I can click on that as well. So we'll just go ahead and select those options and click on continue, and then on OK to get our output. So you can see at the top we've got our descriptive statistics containing the group means, and these means that you see right here, these are unadjusted for group differences on the covariate. So if you're going to be reporting on these means, also make sure that you report on the adjusted group means that are found in the table below under estimated marginal means. You'll see too that we have Levine's test, which is essentially used to test or evaluate for the presence of homogeneity of residual variances. So one of the assumptions of the standard analysis of variance in ANCOVA models is that the residual variances are equal. So in other words, the variances of the residuals across the groups are equal. So basically what you have right here, you have a significance test. If this is significant, which it's not in this case, but if it was significant, then that would be taken as an indicator that you would have a violation of the assumption. The p-value that's given right here is not significant, which is indicating that the assumption is not violated. But you do need to keep in mind that this test that's presented to you is impacted by sample size and also by non-normality on the dependent variable. So you have to consider those two issues when you are evaluating your results. And let me also say that one of those supplemental files that you'll find underneath the video description is this PowerPoint that I have opened up, and there's a little bit of a discussion on one of the slides related to Levine's test concerning when the analysis of variance or ANCOVA results are most likely to be robust to a violation, and in what cases the violation might produce an increased likelihood of type 1 or type 2 error. So be sure to check that out. I'm going to go ahead and just stick with the PowerPoint here just so that it makes it a little bit easier for you to read. And you can see under test of between subjects effects, you've got the test of our between subjects factor, which is treatment group. And you can see right here that we have statistical significance. There's our p-value that's given, and this would be what we would do is infer that there are significant differences in the treatment groups with respect to the adjusted group means on post-treatment anxiety scores. So here's just a little bit of a write-up with respect to that particular finding. You'll also see that under partial eta squared, this is basically an effect size measure right here. If we use Cohen's benchmarks for judging small, medium, and large effects, then this effect would be considered large. This part of our output contains information related to the relationship between pre-treatment anxiety and post-treatment anxiety. So you can see that there is a significant relationship between pre-treatment anxiety and post-treatment anxiety. You can also see the effect size for that would be considered large as well. So following the test of between subjects effects, you can see that we have basically we've got the grand mean on the dependent variable adjusted for the presence of the covariate, and then you also have the group means as well adjusted for the presence of the covariate. You can see right here that down below it's got a little scripting A right there, and it just says covariates appearing in the model are evaluated at the following values, and that's anxiety pre 99.0322. That's basically the grand mean on the anxiety variable. So these means that are found in this table are adjusted for that covariate in the model. Now, if you scroll down a little bit further, you can see underneath those the estimates box containing our adjusted group means, you also see we've got a box containing pairwise comparisons. So you can see right here we've got a column that's reflecting the mean differences. Basically it says I minus J. So the I treatment group minus J treatment group, that's the mean difference between, in this case, the control group versus treatment A. And that's just simply taking this mean and subtracting this mean right here. So that's the mean differences found in this box right here, and you can see there's a significant difference between those two groups. When we compare the control group versus treatment B, that's taking this mean right here and subtracting the mean for treatment B. So there's our mean difference, and you can see there's a significant difference between those two groups. When you compare treatment A versus treatment B, you can see there's the mean difference right there, and you can see that it is not statistically significant. And then finally, when you scroll down a little bit further in your output, you'll find there's the profile plot, and you can see that these are basically, this is a bar chart that's containing bars reflecting the adjusted means for each of the three groups. And you can see the little whiskers in there. It looks like it's basically just that 95% confidence interval around the adjusted means. Now, one other thing that I want to mention, when you're running the ANCOVA, it's not actually in the PowerPoint, but when you're running the ANCOVA, if you were to go under options, if you were to click parameter estimates, then what will happen is the ANCOVA would also be reparameterized as a regression model. So if you wanted to know what the nature of the relationship is between the covariate and the dependent variable, you could get that by essentially obtaining a regression slope for that covariate by clicking on parameter estimates. So just to show you what that would look like, I'll just click on OK right there, and you can see underneath it says parameter estimates, and you can see that basically the B column, these are regression coefficients. So you can see there's the intercept for the model. You can see that right down here there's actually dummy coding of the grouping variable, and group 3 is actually treated as a reference category. But most pertinent to what I'm really focusing in on is this regression slope right here. It says 0.443, and that is essentially the relationship, reflecting the relationship between pre-treatment anxiety and post-treatment anxiety. And the fact that this coefficient is positive is no big surprise. Basically, it indicates that individuals who scored higher on anxiety at pre-treatment also were predicted to score higher on anxiety at post-treatment. And additionally, there's no big surprise, the p-value for this is going to be exactly the same as the p-value that we have in our analysis of covariance table up here for the covariate right there. Now, in the PowerPoint, again, that you can download underneath the video description, I also cover a little bit on ANCOVA assumptions. So just briefly, analysis of covariance makes the following assumptions pertaining to normality of the residuals, homoscedasticity of the residual. That's just basically the homogeneity of variance assumption that I was telling you about. You know, a violation of that can produce inflation in type 1 or type 2 errors. There's also independence of observations as well. Basically, three of the main assumptions related to analysis of covariance itself are that the covariate itself is measured without error. So that's one of the assumptions, and basically if there's noise associated with the covariate that's included in your model, then the adjustment to the group means will be biased. And so in other words, you can end up with biased estimates of group means, and that can have a bearing on your inference concerning differences in population means. A second assumption that's specific to the ANCOVA is homogeneity of regression slopes, and that pertains to the idea that that the relationship between the covariate and the dependent variable is the same across your groups. So to the extent that that assumption is violated, that can also result in biased estimates of group means, basically the adjusted group means, and impact your inference concerning the differences in group means. Another one is that there is the presumption that the relationship between the covariate and the dependent variable is linear. And once again, if this assumption is violated, this can result in bias in terms of the estimates of adjusted group means and ultimately your decision concerning the differences in those means. So at this point, what I thought I would do is just kind of talk a little bit about a couple of the assumptions, in particular homogeneity of regression slopes and linearity, and how to and a couple of ways in which you can evaluate these assumptions in the context of analysis of covariance. So one regarding the test of homogeneity of regression slopes, basically, once again, that assumption is that the relationship between the covariate and the dependent variable is the same across groups. So you can easily do this in SPSS by, after you specified your model, by clicking on this model button right here and then specifying a model where you have the independent variable, the covariate included, and then you have an interaction specified between the independent variable and the covariate. So to show you this in SPSS, we'll go back and we'll go under Analyze, General Linear Model, Univariate. We're going to click on Model right here, and then we'll click on Build Terms. So I'm going to move the independent variable treatment group over, anxiety, basically pre-treatment anxiety over, and then you can see right here it's set at type, and what I'll do is I'm going to highlight both of these and move them over, and that produces an interaction term. And so we'll click on continue and then on OK, and so now in our output you can see that there is a row of information concerning the interaction between treatment group and pre-treatment anxiety, and you can see right here that it's a near significant interaction effect in that particular model. So if the interaction effect is statistically significant, conventionally speaking, then what that would tell us is that the relationship between our covariate and the dependent variable is not constant across the groups. and in that case it would indicate a violation of the assumption. So once again, here we see that the test of the interaction between treatment group and pretreatment anxiety was near significant as 0.056 at the conventional alpha 0.05 level. The effect size might be considered moderate, and then that would lead me to think that there may be some concern about the regression slope associated with pretreatment anxiety exhibiting variation across the groups. So it's also not a bad idea to look at the data graphically. So another possibility is to generate scatter plots and look at the relationship between the covariate and the dependent variable. So you can see right here, I'm just kind of showing you some of the screenshots of steps involved. If you go under graphs in SPSS, go to legacy dialogues, then scatter dot, then select simple scatter, then this box right here, what I've done is I've specified pre-treatment anxiety as on the x-axis, post-treatment anxiety on the y-axis, and then I moved treatment group down here to this box for rows just to give you kind of a visualization. You can see right here that what I've done is I've generated the relationship between pre-treatment anxiety and post-treatment anxiety for each of our three treatment groups, and I've also generated interpolation lines for each group. And you can see visually there might be some differences here between the three groups. So walking you back through it in SPSS, what I'll do is I'm just going to go up to Graphs, Legacy Dialogues, then Scatter Dot right here. I'm going to click Simple Scatter and then Define, and I'm just going to reset that. So we'll move treatment group down to the rows box right here, pre-treatment anxiety to the x-axis, post-treatment to the y-axis. Click on OK. And so now you can see the scatter plots by group. I double clicked on this, and right here it's got add interpolation line. I'm just clicking on that so you can see what the relationships look like within each of the three groups. Now I can also use the scatter plot approach and just generate fit lines within each of the three groups and then look to see if the regression slopes, assuming a linear relationship, are the same or different. And then also I can kind of evaluate the linearity assumption as well, because the linearity assumption is that the relationship between the covariate and the dependent variable is linear within each of our groups. So not only do we have the same slope, but also that the relationship is linear across our three groups. So you can see right here that what you'll notice is screenshots where basically there's our post anxiety scores, pre-anxiety scores, and then there's our treatment variable here, and then you can see that in this scatter plot right here everything is kind of put together, and I'm generating essentially a line of best fit for each of those three groups, and you can see that the slopes for those lines appear to differ. So really quickly we'll just go back to Graphs, Legacy Dialogues, Scatter Dot again, Simple Scatter, and then I'm just going to move treatment group up here to set markers by, click on OK, and so you can see the different colors reflect the different groups. So the control group is in blue, the treatment A group is in red, and the treatment B group is in green. So if I double click on this and then click on Add Fit Line at Subgroups, you can see we now get our regression lines, and I generally don't like having the labels on the line, so I'm going to click off of Attach Label to Line and then Apply so I can see that a little bit more cleanly. So if we assume that there is a linear relationship between anxiety pre and anxiety post, it would still look like that the slopes for those regression lines are all different, which would suggest then that we have evidence of a violation of that homogeneity of regression slopes assumption. Another thing that I can look at is the question of linearity, and I can do that further by clicking on quadratic here or cubic right here and taking a look at any possible nonlinearities in the data. So I'm going to select quadratic right here and click on Apply, and you can see, again I'm going to take that label off, and you can see in this particular case when you're looking at our different lines, you'll notice that the red line, which was treatment A, that hasn't changed a whole lot. I mean, it still looks fairly linear, maybe a shade of a bend there, but not much. This other one here for treatment B, that green line right there, you can see it's still largely indicating a linear relationship, but that control group in blue, you can see that there is a kind of a bowl shape right here, which suggests then that there may be a nonlinearity with respect to that particular group. So it looks like that the relationship between anxiety pre and post appears to be linear in treatment A and B, but it looks like there may be a quadratic trend in the control group. So this is actually something that you would not want to see if you are evaluating the assumptions related to the analysis of covariance. Now, one other thing that you might want to do in terms of evaluating assumptions in the context of ANCOVA is to generate residuals plots. This can be helpful in terms of examining possible violation of homogeneity of variances. That's one possible thing. Also looking for nonlinearities in the data with respect to the relationship between the covariate and the dependent variable, as well as potentially identifying possible outliers. So there's several different things that you can do in order to use the residuals plots in order to evaluate various assumptions. So I'm going to just show you really quickly how to generate them. If you go to Analyze, go back to Univariate right here. Under Save, you can select Standardized Residuals. That's one that I would typically select. You can also select Predicted Values if you want to do this. And so you may be a little bit more familiar with this particular approach in the context of linear regression, but these options are available through the Univariate menu. So I'll go ahead and click on Continue and then on OK. And so now when you're looking at the data set, you've got predicted values on Y, and then you've got the standardized residuals. So if you're looking for possible outliers, one thing that you can do is just simply look at the this particular column right here and screen it for any residuals, standardized residuals, with a value that's greater than say 3. So that's just one really easy way to kind of screen for outliers in our data. So let me go ahead and generate the plot. I'm going to go to Graphs, Legacy Dialogs, then go down to Scatter Dot right here. We'll select Simple Scatter again. I'm going to reset everything right here. So there's actually a couple of versions of the plot we could create. So the first one, I'm going to move standardized residuals to the y-axis right here, and I'll move treatment group to the x-axis. And this is fundamentally what that Levine's test is trying to do using a significance testing approach. So if I do it this way and click on OK, you'll notice that we have residuals for each group. There's group 1, group 2, and then group 3. And so what we're really trying to do is to determine if the spread of the residuals is markedly different across the 3 groups. And if there is a considerable difference, and that might be evidence of a violation of homogeneity of variances. So in this particular case, there's not a whole lot of difference. You do see that there's one case out here and one case out here that seems a little bit more pronounced in terms of the deviation from the mean in that particular group, in group 3, but it still looks fairly consistent across the levels of our grouping variable. Now another approach might be to, instead of using groups on the x-axis, you can actually use the predicted value. So I'm going to move group off here and move predicted value on to the x-axis, and then click on OK. And so really what we're trying to do, what we're hoping for, is a fairly random spread of points across predicted values on the dependent variable. So what we don't want to see is any kind of evidence of any kind of patterning in the data. And looking at this, the spread of points looks pretty random and somewhat constant. Basically, the average of the residuals is 0 right here, and so what we want is for the residuals to be kind of exhibit random and constant variation across or around that 0 point. Now everything looks pretty good in that particular graph, but let's say that I rerun the analysis, and in this particular case what I'm going to do is I'm going to move treatment group to the Set Markers By box, and we'll click on OK. So now you've got the different colors representing the different groups. So if I double click on this and I click on Add Fit Line at Subgroups, ideally, all the basically, the average of those residuals would be 0 within each of the groups. And right now, it looks not so bad. If I click off of this, I'll just click Apply right there, and so you can see it says linear. But let's say that I choose a different kind of trend, like quadratic. You'll notice when I click on Apply that the red line and the green line, both of those, there's a little bit of curvature which might detect a slight hint of a nonlinearity, but the main thing to notice is that blue line, which is for the control group, and you can see that there is a pronounced quadratic trend in that group. So that's further reiterating that problem that I was saying, where essentially the relationship, or essentially the trend, reflecting the relationship between pre-treatment anxiety and post-treatment anxiety, seems to itself vary across the groups, which once again is not something we want to see in the context of an analysis of covariance. So at any rate, that pretty well wraps up this discussion on analysis of covariance. As you can see, the interpretation of the basic results is not really that complicated a process, but it can get a little bit trickier when you are trying to examine various assumptions related to the procedure. And so the main idea here was just to kind of walk you through a few small steps to evaluate a few of those assumptions, but certainly there's a lot more that we could have done in this particular video. But again, I just wanted to kind of keep this a little bit on the shorter and more manageable side. So that concludes this video demonstration, and I appreciate you watching.